Everyone, today we're going to be talking about Physics 252 Week 2 Problem 1. In this problem we are given a bike tire that is hanging on a string from the ceiling, and we are tasked with finding various properties of this wheel as it spins. So getting started with the problem here, we have our bike wheel with mass m and radius r, and it is attached by the rope from one end. As you can see, the center of mass from the wheel is r, and we're ignoring the mass of the axle and spokes, which is important because from this we can decide whether or not we will be using the moment of inertia for a disk or for a kind of hollow disk or cylinder. We're also given that it has an angular velocity of lowercase omega here, and it is oriented along the x direction. So getting started, I think it's important to try to draw a diagram. As you can see, I tried to do the best I could in 3D with this. It is a little bit challenging, I would say, but as you can see, this is our ceiling up here, and we have our rope, and here's our pivot point. This is our axle right here, and this is our wheel. And we note that the wheel is spinning counterclockwise, as it says in the problem here, if you look at it from the positive x direction. So if we're looking at it from this way, it's spinning this way. So that is pretty important later on. So still with getting set up, we know that the force due to gravity is going to be pointing downwards. We know that normal force is going to be pointing upwards along the string, which is essentially tension. And we have, we're tasked with finding the initial angular momentum. So our initial angular momentum for this problem is going to be our L right here. And since L is given by the moment of inertia times the angular velocity, we can kind of simplify this and say that mr squared, which is our moment of inertia for a disk, a hollow disk, times our angular velocity here is our initial angular momentum. So as far as the direction, this is where, in my opinion, it gets a little more fun. So what we can do is we can point our fingers and kind of wrap them around the wheel as if they were spinning in the direction of the wheel. And just in doing that, we can kind of see that our right thumb is pointing outwards along the positive x direction. And from that, we can say that our angular momentum here is going to be pointing in the positive x direction. So this is why I have L here. And since our L is pointing this way, then that means that the angular velocity must point this way as well. So moving on, we have our tension. So tension is defined as our force due to gravity, the cross product of our force due to gravity and our R value here. And if we remember, our value is the essentially the center of mass. So at some point here, but I've drawn it as this vector. And when we cross these two vectors using the right-hand rule, we can see that the torque is actually going into the page. So it's kind of making maybe something like, I guess it would be like this along the negative y-axis. As far as our precession, it's a little more interesting. So precession occurs due to the spinning of the wheel here and its direction. So we have we're starting out with our tension here, which is defined as mgr, and we can use this derivative here as well just another identity that will be helpful, because we can see that we have, I've labeled this vector here as it's spinning is dl. This is d phi right here, and here is uppercase omega, which is the symbol for precession frequency. So what we can do is we can kind of rearrange and try to get this in simpler terms that we can kind of plug into. So what we're going to do is we're going to try to get this in terms of tension and angular momentum. So what I've done here is just kind of gone along the thought process. This is our initial value for angular, or excuse me, for precession frequency. And we can go ahead and, using L and some of these definitions here, we can go ahead along this list, and we end up getting tension over the angular momentum. From here, we can substitute this I out and to get it in terms of mass and the radius. And this is good. We can simplify it here, and this is our precession frequency, but this is in radians. So what we want to do is we want to try to get the precession period. So what we could do is we can divide it by 2 pi. As you can see here, this is our period of precession, TP, and we end up getting this value, or this equation here, for our period of precession. And as you can see, the masses cancel, so we're not dealing with mass in this final equation. But I hope you guys found this video helpful, and thank you very much for watching.